Hello, how's everybody? All right, good. So we are going to introduce a directional derivative today. Let's let z be a function of x and y. So z is equal to f of xy, and let's let p be a fixed point in the domain of f. P is equal to x naught y naught. Let's also fix a unit vector u, which means that the length of u is 1. So the yellow vector in this figure is the vector u. Let's let L be the straight line passing through the fixed point P parallel to the vector u. Now, an arbitrary point on the line L can be expressed as a P plus a scalar multiple of u. So the red point here is an arbitrary point on the line, and it is P plus a scalar multiple of u. So an arbitrary point on the line can be written as P plus HU, where H is a scalar. We define the directional derivative of f in the direction of u at the point P to be the limit as h goes to 0 of f of P plus HU minus f of P divided by h. So notice that if we change the input from P to P plus HU, then the change in the function f is given by this numerator. And h is the amount of change in the input as we change the input from P to P plus HU. So h is the amount of change in the input in the direction of u. So this is the change in f divided by the change in the input. So we can interpret this limit as the rate of change of f as we change the input along the line L in the direction of u. So this directional derivative of f in the direction of u at the point P gives us the rate of change of f, the instantaneous rate of change of f at the point P in the direction of the vector u. Now here's a geometric interpretation of this directional derivative. So the blue surface here is the graph of the function f of xy, and P prime is a fixed point in the domain of the function, and I have drawn so this line right here, that's the line L passing through the point P prime parallel to the vector u. P is the point on the graph of f corresponding to the input P prime. The orange curve here, the orange curve here consists of points on the graph of f right above the points on the line L. So the points on the orange curve correspond to the points on the line L. The directional derivative of f in the direction of u at the point P prime is basically the slope of the tangent line to the curve, to the orange curve at the point P. So once again, the slope of the tangent line T to the orange curve at the point P is given by this the directional derivative of f in the direction of u at the point P prime right here. Okay, so let me now try to explain why that's the case. So again, we are fixing a point P prime in the domain of f, and we are going to be interpreting the directional derivative of f in the direction of u at the point P prime. The blue surface again is the graph of f. P is the point on the graph corresponding to the input P prime. L is the line through P prime parallel to the unit vector u. The orange curve, the points on the orange curve corresponds to the points on the line L. So the points on the orange curve are the points on the graph of f right above the points on the line L. So here we pick a point Q prime on L where Q prime can be expressed as P prime plus a scalar multiple of u. So Q prime is equal to P prime plus HU for some scalar h. And Q is the point on the orange curve right above the point Q prime. Let's look at the line between P and Q. What is the slope of the line PQ? Well, we need to find the change in height from P to Q. What's the change in height from P to Q? I'm calling that delta Z. Well, that's going to be the height f of P prime, so that would be the height of Q minus the height of P. Now what is the height of Q? Well, the height of Q is basically f of Q prime. F of Q prime is the same as, where Q prime is the same as this. So the height of Q is f of P prime plus HU, and f of P prime is the height of P. So f of P prime right here. So this is the change in height from P to Q. And then if we divide that by the amount of change in the input in the direction of u. So this h is the, so here we are changing the input from P prime to Q prime. So h is the amount of change in the input here. So if we divide the change in height by the change in the direction of u, so that's going to be the slope of the line PQ. Now notice that if h goes to 0, then the orange point here will go toward the point Q, point P prime, and so the Q will go toward P. So the line PQ will merge the tangent line here. So if we take the limit as h goes to 0, then we're going to get the slope of the tangent line T. So what we see then is that the directional derivative of f in the direction of u at the point P prime is giving us the slope of the tangent line T to the orange curve at the point P. Okay, so I hope that made sense. Now, if I have a function of the directional derivative of a function of three variables is defined the same way as we did in the case of two variables. So here is another interpretation that I want to give here. So imagine that the graph of f, which is the blue surface, is a mountain, and we are hiking on this mountain, right? So right at the point P, from the point P, so let's say we are standing on the point P, and if we are walking in the direction of the vector u, then the directional derivative gives us the rate of change of elevation, right? So as we walk along the in the direction of u, then this is giving us the rate of change of our elevation. So that's one way to interpret this directional derivative. So again, the function f gives you the height of the graph, so you can say that this is the rate of change of height in the direction of u. Okay, so I'm going to stop here, and in the next video we will see how to compute directional derivatives.